Once again, hello, ladies and gentlemen. My name is Albert Marroquin, and I am the Dynamics and Safety Engineering Division Manager at ETAP. I have been working in the Dynamics Engineering Division for over 15 years, and my experience has been mainly in the design and creation of controllers, exciters, governors, and power system stabilizers. Today, I have the pleasure to share with you our webinar topic, which is titled ETAP 16 User Defined Models, or otherwise known as UDM. The enhancements that we have added to ETAP 16 are tremendous, and it is truly my pleasure to be able to share that information with you today. Before we get started with technical examples that I will use to showcase some of the new capabilities in ETAP 16, I would like to provide a high-level overview of the topics that are included in this webinar. Part 1 of our webinar will focus on the interface improvements, which were created for the purpose of enhancing the performance and speed of the model development and troubleshooting. After that, I will continue by showcasing the calculation features and enhancements which make the calculation engine more powerful in ETAP 16. And last, I will proceed to show new communication levels and plant level control schemes which can be executed with the new capabilities of ETAP 16. All in all, this webinar has several application examples which will provide educational and instructional information for the benefit of the audience, and at the same time will introduce the usage of some of the new features in ETAP 16. Before we jump into our technical examples, I would like to give you a quick outlook of the part 1 of our webinar. In this section, we will focus a lot of our attention on the enhancements related to the test routines. The existing test routines from ETAP 14.1 were significantly enhanced in several ways. One of them was to allow for user-definable inputs which are taken into the simulation to better allow us to analyze the performance of our newly created models. At the same time, ETAP 16 UDM in standalone mode received a new simulator which allows us to simulate any kind of transient condition within the system without the need to execute it in the transient stability engine. This gives us a whole new dimension of simulation capabilities because we no longer have to test and simulate the events exclusively through the transient stability engine, which at times could be very time consuming. All in all, the enhancements to the test routines and the new simulator are perhaps the most important enhancements that the UDM tool received in ETAP 16. So let's begin with our first example, where we will talk about the enhancements to the test routines through an example using an excitation system. The excitation system that you see on the screen, it's a new exciter which is published in IEEE 421.5 2016. This is a new excitation system standard which was released a couple of months ago. We are currently working on the addition of all the models of this excitation standard, and they will be added as UDM models using the new ETAP 16 features and capabilities. In the upcoming months, ETAP will release a whole new library of excitation systems using the documentation provided in the standard. I myself will be involved with the development of models such as the one that you see on the screen, which will help our users have off-the-shelf models to perform their transient stability simulations. As we can see on the screen, the new features and capabilities that were added to ETAP 16 are actually highlighted in this example. I will discuss in a lot of detail in the future during this webinar I will talk about some of the new elements that are highlighted and their purpose. However, in this transfer function, we can observe already some of the new capabilities like the go-to blocks, the actual script block examples, as I'm highlighting on the screen, and also some of the new mathematical blocks like the multi-input, multi-output blocks, and so on and so forth. There are a lot of new elements and capabilities that I will highlight in the future. However, for this purpose of the presentation, we will talk a little bit about the enhancements to the test routines. For the excitation systems and for governor systems in ETAP 16, we redefined the way the test routine is executed. First, we added a new simulation capability which is called none, and it extends for an actual low flow event or an event where we expect the excitation system or governor system to reach steady state conditions. This test was designed to simply observe if our exciter can reach steady state conditions and remain in those conditions throughout the duration of the simulation. Steady state operation is an important part of our analysis. We must ensure that the system reaches steady state conditions before we introduce any transients. Let's take a look at how this simulation works. By simply selecting the none event from our parameters section, we can proceed to translate the model or compile it. And as soon as we do that, we can quickly run a simulation that will show us the result of this event. We can quickly zoom in and observe that indeed our excitation system has reached a steady state value of approximately 1.6 per unit, and it remains in steady state condition, which tells us that this model is able to start and stabilize and reach its transient steady state operational point. At the same time, in ETAP 16, we also enhance the existing simulation events. For example, if we focus our attention now onto a load shedding event, you will notice that you can still select it in similar fashion as in ETAP 14.1. However, now we have control over the event time, which is something we did not have control over in ETAP 14.1. The event time can be defined by changing the value as indicated in this parameter section. At the same time, we also have added in ETAP 16 the ability to specify the total simulation time. I will change that value to 6 seconds. And let's observe what happens with the plots. As we can see on the screen, now we can define the time at which we perform the load shedding event. We observe the transient behavior, and we observe that the exciter output voltage settles onto a lower value than the initial value. 1.6 initial value, and the final value is roughly approximately 1.55 per unit. In addition to the event time and the specification of the total simulation time, we have added the capability for a plot step, which is very important. Let's use as an example now a fault condition, where we will study the fault performance of this exciter. This exciter happens to be an IEEE 5C excitation system, which is a terminally fed exciter. It draws its power through the terminal output voltage of the generator. In this case, the fault event will place a fault at the terminals of the generator, and therefore our terminal voltage will become 0. We would expect the exciter output voltage to follow the terminal voltage trend during the fault conditions. We can observe that. At the same time, what I like to do is I like to reduce my plot step to the smallest plot step available to be able to observe all the details that our graphical response will provide. Indeed, we can observe that during the time that we have the fault, which is introduced at 2 seconds, its duration is approximately 700 milliseconds, and then after the fault is clear, the exciter starts to provide output voltage and goes to its transient, hit its ceiling voltage, and then starts to return back to the original steady state condition. As you guys can see, the simulation time has been tremendously improved. This is something that we worked a lot in ETAP 16, and I will talk more about that in the future. I just wanted to highlight that at this time. It takes a couple of seconds for these plots to open. It's very, very fast operation in ETAP 16. So to recap, the test routines were added. We added event times, we added simulation time, plot steps to allow for more control of the testing that is performed during the troubleshooting stage of a UDM model creation. The last item that I would like to highlight is that we allowed for the definition of input values which are taken from the system. In this case, we could define the initial voltage at the output bus of the generator, so that the exciter will regulate the voltage to that desired value upon initialization. And we could also define items like the input frequency, which is an external parameter fed into the generator. Making those changes allow us to define the initial conditions in better fashion to complete our tests during the simulations. Now we will move on to a different example where I will explain the closed loop transfer function that is used to generate the transient events that I have just highlighted in this section. Many times we have problems to initialize and reach steady state conditions during our troubleshooting and development of these UDM models. I would like to show you with some examples what is it that this test routine does in the background, and how you can use some of these new capabilities in ETAP 16 to troubleshoot your systems in a better way. So let's take a look now at the inside mechanics of an exciter and a governor test routine. Let's start with the exciter test routine, in which we can observe a transfer function diagram. I created this transfer function diagram as an example that I will give to the listeners of this webinar. After the webinar, we will make sure that we take requests on links on where these models that are provided with this presentation can be downloaded. These two examples for the excitation system and the governor can be used to test and troubleshoot the excitation system with a test routine inside mechanism exposed. Therefore, we can use it for troubleshooting, like I said before, initialization and other type of simulation problems with our control systems. The diagram that we have on the screen represents an exciter test system transfer function. It has three main areas. It has the exciter control and the output field voltage point, where it would actually generate and excite the generator, which is a simplified generator system, which is represented by the internal voltage, the generator reactance. Connected to its terminal is also a variable load, which is what we controlled in the test routine to achieve the different disturbances that you have observed from the previous section. In this example, we can perform a low flow, a load rejection, a load acceptance, and a fault at will. The test event simulator is the last area of this user definable model that we created in ETAP 16. It indicates how and where we can place the different disturbance events. By entering the event type and the event time, we can place a disturbance at will in the system. As we can see, we have an input that defines the generator internal impedance, and we have another input that defines the initial and final load that is going to be applied to the generator system. At the same time, this transfer function closes the loop, which is something that we did not see before in the previous example. We take the terminal voltage output and the terminal current, and both of those signals complex terminal voltage and complex terminal current can be used as feedback signals into our excitation system, which will then take those signals and adjust them to the desired output voltage on the exciter. This is the closed loop system that is used to test excitation systems when we run that in the built-in test routine. Let's do a quick simulation event. In this case, the test routine is configured to do an event type number 3, which stands for a load acceptance. In ETAP 16, with this off-the-shelf standalone simulator, all we have to do is translate our model and quickly execute the simulation. At this time, I would like to introduce another new feature of ETAP 16 UDM. The plotting capabilities in ETAP 16 UDM were tremendously enhanced. We added the ability to automatically graph the data plotters, or otherwise known as scopes. These elements allow us to plot and visualize the output values throughout different internal parameters in the UDM model that we have created. In this case, we have automatically generated approximately 10 plots, which were generated in less than a second. The event that we created was a load acceptance, and in this case, as we can see, and the electrical power, if we zoom in, we can observe that we started with an initial value and we added electrical load to the system. The graphics show the transients experienced by the simplified generator, the initial and the final output on the electrical power. In the excitation system that we are testing, perhaps the most important graph that we are looking at should be the exciter field voltage. Using this chart, I will focus on a couple of things. The first one, I will show you what happens during initialization of an actual excitation system. As can be seen on the screen, in general, our test routine has to start our transfer function initial states from 0 values. And during a specified amount of time, which could be usually 30, 40, or 50 seconds, we allow the exciter to reach its internal states and finally reach the desired steady state operational value. This process is what we call as internal initialization, and it is something that we can observe graphically in this image, and it's something that occurs in the background in the test routines that we have built into the program. Many times during this initialization process, we may hit some nonlinear conditions and reach clamp values, which prevent the internal states of the exciter from reaching its desired steady state values. This will produce what we know as fail to initialize problems in the model. And this test routine transfer function that I'm providing with this webinar can be used to observe the internal states and the behavior of the element during excitation, and also help you to correct the problems by identifying them. So now that we've talked about the initialization process, let's see what happens with the rest of the simulation. In fact, we can observe that the exciter reached steady state conditions, and then at a specified time of approximately 50 seconds, we go ahead and add an event to this element. So this is the event that we added there, where we have the addition of the load to the system. And we can confirm initial and final excitation values. Before we move on to the governor system and to see how that one is configured, let's do one more final simulation for the excitation system that we have selected. In this case, let's go ahead and change our event type to event type number 4, which will represent a fault with a duration of 700 milliseconds. we can quickly take a look at a couple of plots. We can see at exciter field voltage during initial conditions and during the actual fault event, and confirm that in this case we are dealing with a different type of exciter. This must be an alternator source excitation system because its output exciter voltage does not depend on the terminal voltage during the fault. That can quickly be observed. At the same time, we can add scopes and plots throughout the simulation and observe the behavior of other important points, which is something that we cannot do in ETAP 14.1. In this case, we can observe the terminal voltage and indeed confirm that during the fault the terminal voltage goes to 0, and then after the fault is cleared the voltage goes through its transients and returns to pre-disturbance steady state operational values. Another thing that we can do in ETAP 16 is we can utilize the data and export it to third-party applications like MATLAB Simulink or Microsoft Excel. That's another new capability in ETAP 16. We could do such an export operation by simply right-clicking on the chart and selecting the Save option. As soon as we do that, the program automatically exports the data to Excel in a format which includes the time step, the simulation time, and the actual parameter that is being exported, using the name given to the data plotter and the signal being fed into the input of the data plotter. This is very important labeling capability as well. That way we can clearly and quickly identify the data that we are exporting to other applications. Once we have sent the data to Microsoft Excel, we could quickly insert and generate a plot for our results. Another new capability that we have added to ETAP 16 is the ability to close all the plots and open all the plots at will. By simply clicking on the close button or icon, we can close all the plots active in the particular model, or we can click on the plot test results and bring them all back to view. This is very important. It's a very important capability to be able to manage a large number of plots which are generated during our simulation. Let's proceed to take a look at the governor system. The governor system is similar to the excitation system in a sense that we have a closed loop transfer function that we must use to generate the feedback signals to test our newly created governor and prime mover system. In this example, we have a fuel system, a turbine used as a prime mover, a governor and speed control element, and we have a electrical system that represents the load added to the generator. We also have a mechanical model which could be a single mass or a two mass or a multi-mass model, depending on the complexity and the test and the type of study that we want. In this case, we're utilizing a single mass model which comprehends the prime mover, coupling gear, and generator inertia all combined. As we can see in this diagram, we have behind the images the elements that represent the fuel system, the combustion, and the turbine. We also have the elements that represent the governor and the speed control. And last, we have the elements that represent the single mass model and the acceleration, torque, and the load torque, and the mechanical power that is generated by the turbine. Using this very neat example, we can again duplicate the simulation plus get the benefit of controlling the event time, simulation time, the inertia using the system, and in being able to also observe the internal states used in the system. I would like to take the opportunity to show you a couple of examples, including one which is a common issue in which we may have failure to initialize, and I would also like to share with you how to handle that condition. First, I would like to start with a simple load rejection simulation. In this case, we're going to configure our action for a load rejection as number 3, but this time by specifying a parameter to the model parameters section. We can quickly launch our simulator, and we can observe very quickly that we would utilize for this test a constant electrical load model, which starts with 1 per unit load and then immediately sheds at 30 seconds 50% of that initial load and lets the system run for another 10 seconds after that. We can take a look at a couple of very important plots. The first one, and the most important one for this prime mover system, is the mechanical power output of the prime mover. In this case, just like we saw in the excitation system example that I did before, we can see the initialization process and see how we start from initial 0 states and we build our desired initial steady state operational mechanical power. After that, we've reached the steady state point at 30 seconds or 35 seconds approximately. We proceed to do the load rejection and we observe the output of the mechanical power in the system. Another important plot is the rotational speed of the system during and after initialization. We focus on this portion. We can observe that the speed of the rotor and the mechanical system is building up until it reaches its desired value, and then finally it actually settles into the final value. Next, let's take a look at the simulation that I mentioned we could use to explain a failure of initialization message during a governor test simulation. For the purpose of this example, I would like to change the action and the simulation time to better be able to observe the results through the graphical data plotter outputs. In this case, I will utilize a simulation for a load acceptance. I will also use the new total simulation time capability in ETAP 16 to change the total simulation time to 60 seconds. At the same time, I am going to reduce the plot step to 10 times the time step, and our time step is configured to 2 milliseconds. After making those changes to the simulation time, time step, and plot step, and the event type, I would also like to introduce a nonlinear limit into our fuel system for the prime mover. The reason we want to do this is so that we can observe what could happen during an actual troubleshooting process of a governor. So I will proceed to change the the governor fuel limits to 0.56 per unit. And now that we have made a change, we can simply compile and run our simulation and observe what happens with the results. Let's take a look at the mechanical power first. We can observe the initial outputs start at 0 and build up to a value of approximately 0.5 pu. At 30 seconds, we cannot longer support the additional load, and therefore we have a clamped out mechanical power. Proportionally, that would result in a collapse of the speed of the rotor, which never reaches its desired 1 per unit steady state value. This would result in the test routine failure to initialize and an error message or warning message being displayed. For those of you who are familiar with ETAP 14.1, you would then proceed to start to troubleshoot the system by making changes. This test routine could be used to quickly identify the issues with initialization. Let's make a couple more further changes to this simulation. First, let's change the event time to 60 seconds, and let's change the total simulation time to 100 seconds. And quickly observe what happens to the new results. The speed plot, we can quickly observe that it almost takes 60 seconds for the governor to reach its operational speed close to 1 per unit, and as soon as we add the load and we over exceed the mechanical capability of the governor, the speed starts to collapse and reduce down to small values or 0. We can observe also the load rejection and the failure for the mechanical power output to increase, and what occurs with the governor during that transient event. All in all, this tool and this transfer function can be used to troubleshoot our governors and exciter systems to help us have an easier time in the creation of and troubleshooting of our governor systems. The final simulation after I removed the limit shows us that we are now able to reach the final output of 1 per unit after we add the mechanical load to the system. Our next example is one in which we will discuss the capabilities of UDM as a generic tool to create any kind of load or source machine model. This is a very important capability because different industries like renewable energy systems and microgrid systems are introducing a lot of new power system components which we need to model, and we do not have we may not have built-in models in ETAP for their use and simulation and transient stability. The UDM tool can be used as a tremendous feature to create these new models and be able to test them and use them for complex simulations in power systems. The next example that we have prepared for our webinar will show how ETAP UDM in version 16 can be used to create complex machine models. The diagram that we see on the screen represents how we can use the UDM tool to create a starting device, a drive which can control voltage and frequency, and also how we can use some of the new tools in ETAP 16 to create machine models like wind turbine generators or induction motors or other types of machines within the UDM generic load/source element. This diagram shows a few main components that can be observed right off, like the speed controller, which is a proportional integral element, which after the drive executes the motor start will take over and control the drive frequency and speed to operate the motor at different operational speeds. We also have a group of elements which represent the drive and the controls to the drive, which apply voltage and frequency commands for our drive output to start and operate an induction motor model, which is represented by this group of elements in the screen. After the motor starts generating electromechanical torque, this electromagnetic torque generated at the output at the air gap will then drive the rotor and its mechanical load. This next group of elements represent the rotor, shaft, and load inertia coupled together, and they also represent the load which is being driven by the motor. The load could be different types of mechanical systems like pumps, fans, and other types of elements. In this case, our example is a motor that is driving a pump. This example is actually a very complex system of equations and electromechanical relationships, which will determine the acceleration time and the speed of the motor under different starting device conditions and voltage and frequency changes. However, the main element that we can introduce that was added to ETAP 16, which makes all of this possible, is the script block. And the perfect example to show the power of the script block is the motor electrical circuit block. The entire equations or set of equations which represent the electrical characteristics of the machine or the motor model were coded into this script block. So what we could do now is simply double click on this element, and we can observe that it opens a generic script block editor in which we can define all the logic and equations which make a model for an induction machine. The language used for this script block is C#. C# statements can be added into individual sections of the block, which are predetermined and pre-configured when we add one of these new script block elements into the system. As we can see, our script block has using namespace and class definitions, which allow us to have off-the-shelf commands and tools which we can use during the coding of the mathematical function inside of this block. At the same time, our script block consists of three main sections. One of the sections is a general definition for variables. Another section is the test routine and initialization, and the last section is the actual running mode mathematical function that we are defining. Our ETAP 16 user guide has a complete explanation onto how to utilize each one of the sections. However, for most purposes, after we add a UDM script element, all we will have to do is actually make the changes into the simulation routine section, which I'm highlighting at this moment. As we can see, we have defined all the equations that relate the slip, the input voltage and frequency, and eventually end up in resulting in the calculation of the motor impedance and the motor torque, which will then be sent as an output of on the output of these script blocks. This block pretty much opens up an unlimited number of potential applications for the UDM tool, and it allows us to customize and create any kind of mathematical or logical function by the use of C# statements. The final output of our motor model is the motor torque and the motor current. So now that we have explained how this script block works, before I actually run a couple of simulations on this complex drive model that I have created for this presentation, I would like to show you how we can just drop a block and how the generic off-the-shelf code is already part of that element. In ETAP 16, we have a new block called script, and if we click on it and simply drop it anywhere on our diagram, we could then proceed to quickly define whether we'll have multiple inputs up to 10 or whether we'll have multiple outputs up to 2. So this creates a tremendously powerful element which now can have up to 10 different inputs and 2 different outputs. And once we open its editor, we see that pretty much all the statements have already been predefined, and all we have to do is now specify the mathematical function that describes these blocks. Some sample code has been added for our usage, and then at this point we could insert or create any kind of mathematical function such as u plus U1 plus U2, etc., etc., and then populate the output or create any kind of mathematical relationships. If our coding is correct, we could use this script block editor test code to determine if our code is and syntax is fine, and if it is, it will automatically apply a test routine, which is predefined as another section in this block, and it will use the inputs on that test routine, which are user definable, to check the code that we just generated. At the same time, if for some reason we omit some characters and our syntax is incorrect, our test code tool will also help us to determine what could be the problem, and it will give us some suggestions on to how to check the code and the syntax that we used. All of these tools make this for a very powerful user definable script editor, which can be used to create any kind of mathematical function. Now we can remove our newly created element and go back to the predetermined example that we have on the screen. This particular drive has been configured to allow for a bypass, which will then take or operate the drive as a starting across the line element. The drive has also been configured or programmed to perform a variable frequency drive and also a variable frequency drive motor start operation, followed by a frequency control, which will then take the speed of the motor to different operating set points. So to see the most interesting of these simulations, we can start directly by modeling only a couple of them. I'm going to model the variable frequency drive start, followed by the variable frequency drive with a speed control attached to it. All we will have to do, as we've seen in previous examples, is change the properties of our block, which indicates the action or events or controls that shall take place. In this case, the starting mode selector can be configured in our example to starting mode 3, which is a variable frequency drive with a ramp with constant volts per hertz of 2 seconds. Now that we've changed our selection, we can translate and compile our model, and super fast we can run and get the results on the screen. In a matter of seconds, we've gone through a matter of 10 seconds of simulation, and we can see plots like the motor speed, the slip, the input frequency, the input voltage commands to the drive. We can observe the motor current, and then we can see plots like the acceleration torque, the load torque, the acceleration torque in the motor, and finally the motor torque. So a variety of plots are automatically opened like we saw before, and we can then study to see if indeed our motor operates as a variable frequency drive. We could quickly observe the output of the slip plot and determine that with this variable frequency drive application, our slip goes to close to rated slip in less than a quarter of a second. We could also observe that it takes approximately 2 seconds for the machine to accelerate to rated speed. We could also observe the motor current as it appears at the output of the drive, and we can see how the current is limited to around 1.25 per unit during most of the period of acceleration of the machine, which is one of the main benefits of the variable frequency drive start. Following this, we could observe the remaining motor plots and acceleration torque plots and so on and so forth to continue analyzing the operation of our induction machine with a customized drive. So now that we have observed this behavior, we could proceed to close all of our plots and take a look at the interesting simulation for the case where we follow our variable frequency drive start with a switch to a constant speed controller operation. With a simple reselection of the operating mode, I can then take our drive and now apply a volts per hertz start similar to the one that we just created. However, in this case, as you guys can see in the screen, we are applying other transients on after the motor has been started, and we can see the effect on the acceleration power and the motor torque. We can see the motor current, and then we can see the input frequency and the input voltage commands to the drive. Now let's take a look at the motor speed real quick to observe what's going on. As we can see, our variable frequency drive starts the motor at around 1.5 seconds, and then after a little bit less than 2 seconds the machine has rated operational speed, and somewhat throughout at around 6 seconds the machine controller takes over and starts to operate and change the speed of the motor. In this case we're simulating a 10% drop in the motor speed, and we can observe how the speed goes from approximately 0.98 per unit RPM to approximately 0.88 per unit RPM. In this case we have successfully applied a variable frequency drive followed by a transition in the motor speed through our motor controller drive. Taking a look at the current, we can observe the transients which will occur at the output terminals of the drive and the motor current that is drawn by the machine based on the variant voltage and frequency. And we can observe how the current goes from its pre-disturbance operational speed to the final value. And we can zoom in to see more details if required. And last, we can observe how the machine undergoes a large deceleration torque once we introduce the reduced frequency and voltage. In essence, we see the rotor undergoing a large deceleration force to slow it down and bring it to a lower operational speed. We could confirm the same thing by also looking at the slip, in which during the time that we apply the reduction in frequency, we can see that the slip becomes less than 0, which indicates a deceleration effect on the rotor. All these things being said, we have managed to create a very complex motor drive and induction motor using equations that are built into new components in ETAP 16, and then we could then utilize this drive and test it inside and utilize its benefit in the transient stability simulation. By simply going back to transient stability, we could select our model, click on the OK button, and now we have added the equivalent of a built-in large drive and induction motor into a generic load element in ETAP. And once we run a transient stability simulation, we could observe how this element behaves and how it impacts the rest of the system, which is the most important aspect of a transient stability simulation. We can quickly step to the simulation, and we can observe how this drive interacts with the generator in our system. You can look at the motor active, power demand, and the current. And now we can confirm that indeed our drive starts the motor, and we can see the transients that it applies after the machine switches to a speed control mode. This will be a new modeling capability which cannot be handled at this time by our built-in variable frequency drive. This will be the drive current on the input side of the drive. So to summarize this example, we've seen now how UDM can be used to create any kind of dynamic machine model, whether it will be a source or a load. In the future part 3 of this presentation, we will show how the UDM models in ETAP 16 can be used to create source models for wind turbines and other kinds of elements. I would like to continue next with the showcase of the second most important enhancement to ETAP 16 UDM, and that is the performance of the program. In ETAP 16, we essentially redid the entire engine, and we enhanced the speed and the memory allocation for larger models. The results of the speed performance are outstanding, and we can see up to 50, sometimes even higher than that, times faster simulation times. Here I would just like to spend a couple of minutes to highlight how with ETAP 16 it will require a lot less engineering man hours to simulate and perform a lot of dynamic calculations. In this pre-recorded video, we can see how a comparison of ETAP 16 versus 14.1 for the standalone simulation tool in UDM. As we can see in this video, it took slightly less than 18 seconds to run ETAP 16 from the standalone tool, compared to almost 10 seconds plus for the ETAP 14.1. This is over 20 to 50 times faster performance. This means that if we use ETAP 16 to troubleshoot and create models, we should be able to develop models 3, 4, or even 5 times faster than before. However, on the performance side, the most important aspect is how fast transient stability systems run with a lot of UDM models. In this example, we are comparing also ETAP 16 versus ETAP 14.1, and we can observe that the performance of ETAP 16 is also far superior. As we can see on the left hand side, ETAP 16 has already finished a transient stability simulation with 6 UDM models in it, and on the right hand side, ETAP 14.1 continues to run and run and run. Eventually, the transient stability simulation in ETAP 14.1 will probably take over almost a minute or a minute and a half to complete. This means that a lot of the initialization time and the running time which was done in ETAP 14.1 has been reduced, and therefore ETAP 16 has far better performance. This will reduce the time that it takes to run each individual transient stability simulations. The last section of our webinar today revolves around a couple of application examples which can now be executed because of some major enhancements to ETAP UDM. The first enhancement is the go-to block, which can create communication channels between UDM models in transient stability. And the last enhancement to ETAP 16, which we will discuss in the next two application examples, is the enhanced interface between transient stability and UDM to handle current injection models for wind turbines. First, let's start by taking a look at the input-output blocks in an example in ETAP. The system that we see on our screen represents a small microgrid, which is composed of wind turbine generation, photovoltaic systems, diesel generators, and inverters and battery stations, which take the job of an energy storage device. By definition, a microgrid is a power system which can operate in islanded mode. Not connected to the grid to have its frequency and voltage support, it must be able to operate through transients introduced by the renewable energy sources in the system. In ETAP 16, we have added the ability to simulate a master controller and how that master controller can control the generation, the load, and the removable or loads that can be shed from the system. All those decisions are made by a special master controller which can be created and which can take advantage of the new go-to blocks which were added in ETAP 16. These go-to blocks can create internal communication channels, or they can create external communication channels which allow UDM models to communicate and transfer set points and operating points. At the same time, the models can transfer information which can be used by the transient stability engine to generate disturbances in the voltage, frequency, and generation in different components in the system. In the screen we see a master controller which can take operation for load shedding, can execute wind turbine transient simulations for reduction or increment in the wind speed, or it can also apply generation control to the diesels. It can make them operate in isochronous load share or in other modes of operation. The master controller takes the inputs from the wind turbines generation and it sends outputs to it to determine what amount of generation we need from the renewables. If we inspect the wind turbine models which are integrated into this system, we can see that we have power commands which come from the master controller on the left hand side, and on the right hand side we have the generation for both active and reactive power which is sent back to the controller. The controller can then determine what the reference set point will be for the generation of these elements. At the same time, in this example, we have energy storage elements which monitor the system frequency and receive commands from our controller to either enable or disable the energy storage device during different generation conditions. At the same time, we have received the state of charge and charging set point for the battery to determine how much active power to charge the batteries with. All these controllers are simply integrated into the transient stability elements and allow for communication and control of the system. We can run a quick simulation to see an example of a transient wind condition on the wind turbine elements in our system. The go-to blocks are a tremendous enhancement to ETAP 16 because they open up for different plant level types of simulations where we can implement automatic generation control, microgrid, or grid interconnection studies. As we will be able to see in this simulation, what we just executed is in essence a simple low flow event. There is nothing indicated through the study case. Everything in the simulation is being controlled by the master controller inside of this UDM element in the control center. We can take a quick look at the plots for the wind turbines to see what is going on. We open a couple of the plots and look at the active and reactive power, and we can see quickly that the wind turbines underwent a reduction in wind speed and therefore generation down to no output, and then after almost a minute of no output the wind returns and the generation goes back to the pre-disturbance condition. We can see also the effect on the reactive power demand of the wind turbines during this low wind transition period. Of course, this study, the main aspect of this situation would be to determine the frequency of the system during the generation change. We could look at the substation bus where we have our master controller and observe the voltage and the frequency that is being monitored by the master controller. The master controller would then take the frequency readings and determine if, based on the frequency, it needs to add or remove load by the control of the energy storage device. Our final graph in this section will represent the energy storage device. Which shows that it either charges or discharges active power into the system as the frequency changes. This element will then improve the frequency performance of the systems during transient wind generation conditions. Our next example will now focus on how the new tools in ETAP 16 UDM can be applied to wind turbine simulations. Now we can go to our last application example for this webinar, which will be a wind turbine interconnection study project. In this system, we are representing a wind turbine interconnection study. We are using a 100 megawatt aggregated wind turbine system, which represents the entire plant. That element is interconnected through a collector system represented by the transformer, impedance, and collector system. It uses a substation step-up transformer, which will then interconnect at the point of interconnection bus 2 with the grid. In this system, we have represented the wind turbine using a UDM model created in ETAP 16, which uses again a lot of the new capabilities like the multi-input mathematical block. It also uses the go-to blocks in internal mode of operation as well as external mode of operation, and it also utilizes the new current injection inputs for the voltage and current injection outputs for the terminal current of the wind turbine generator to allow it to simulate current injection simulations required by different interconnection standards and models. That gives you a high-level picture of the wind turbine model. At the same time, this particular system received a diagram which represents the interconnection, active and reactive power requirements for a particular grid. In this case, an example from a German interconnection grid standard was added and built into the model so that we could simulate the reactive power demand during an interconnection study. So overall, this model is a wind turbine type 4 model, which is a full converter wind turbine model, and we are modeling for the most part the inverter and its interaction with the grid system and the inverter controls. We can proceed to run a couple of simulations for the purpose of this example. The first simulation will be a fault in the collector system, and we're going to see how the wind turbine responds to that fault. So after we've compiled our wind turbine model in UDM, we can proceed to run the model in transient stability, and we can evaluate the performance of our wind turbine under fault conditions. In this case, we have put the fault at the last point of interconnection bus 2, and we can observe how the wind turbine output, wind turbine active, reactive power, and the terminal voltage react towards the fault. In this case, we can see that the voltage at the terminal of the wind turbine goes down to around 0.2 per unit. We could also see that during the time the fault is in place, the wind turbine injects reactive power towards the fault. The current injection model allows UDM in ETAP 16 to handle much better current injection situations during low voltage conditions. Last, we can observe the reactive power output, the real power output of the wind turbine during the fault. By analyzing these results, we can see that our wind turbine model in UDM is under steady state conditions before the disturbance and after the disturbance, and the values are the same. This is a good sign. It means that our model is stable and it can ride through this fault condition in the system. Now we can do a final simulation of our wind turbine system where we can represent the interconnection study and how changing reactive power demands will be based on different active power injection into the utility or network. Before we can run that simulation, we must make a couple of changes to our diagram where we'll inject, instead of single reference generation, we're going to inject the reference map for the interconnection requirements. A simple change on our switch blocks at these two locations will allow us to pass the new reference values. So now we can proceed to run the highlighted portion in yellow of our interconnection requirements, which will start to inject active power from 0.2 per unit and finish at 1 per unit, or 100% of the wind turbine generation capacity, and it will observe whether we can meet the total full load demand reactive power of approximately 0.4 per unit. Once we make the change to our wind turbine, we can go back to transient stability, and we can rerun now a simulation where we can observe what happens to the reactive power injection of the grid and whether it meets our requirements from the grid. As this simulation runs, you guys will be able to observe that the reactive power output increases and that it does finally reach the required output of the interconnection study. We can look only at the active and reactive power output. Indeed, we can see that as the controller steps up the power injection from 0.2 all the way up to near 100% active power, we can observe that the reactive power output generated by the inverter finally meets the final required value of approximately 40 megawatts. This kind of study would be repeated under different generation conditions and under different voltage and frequency values on our interconnection network. We could do a final simulation where we could see what will happen if our wind turbines were not capable of supplying the required reactive power into the network. For that purpose, we can go to the reactive current limitation part of our circuit, and we can make an adjustment to the steady state reactive power output limit of our wind turbine. Once we change the reactive power output limit, we can retranslate our model and observe what would happen on the transient stability side and determine whether the same simulation that we just ran a few seconds ago will still meet the requirement of interconnection. At the same time, instead of looking at the output of the reactive power as we did in the previous simulation, we will take a look at the output at the substation transformer primary side, or the power that is sent into the network at the point of interconnection. We can open our plots and go to the branches and pull up the plot for the station transformer and look at the megawatt megavar charts for that transformer. And immediately we can see that the branch real power is injected as same as before, from 0.2 to nearly 1 per unit output power, or almost 95 megawatts. However, we can see that our reactive power requirement at the point of interconnection failed, because we can see the rejection at one of the loading points on the wind turbine output. We can observe at each stage previous to the last stage, the reactive power output reached the desired operating value. However, on the last output at 100% active power generation, the reactive power capability of the wind turbines could not suffice and reach the final desired value, which is approximately 40 megavar. In this case, you could use ETAP UDM to simulate other elements, or perhaps we can just simply explore the possibility of adding capacitors or static VAT compensators and other elements which would supplement the reactive power capability of our wind farm. This would conclude the last application example that highlights all the new features of ETAP 16. In conclusion, we would like to say that ETAP 16 UDM performance improvements have provided a significant reduction in the amount of time that it would take engineers to perform dynamic studies. The speed improvements and the larger memory capability and the speed of the plotting are tremendous features which will reduce the time it takes for troubleshooting and creating dynamic elements. At the same time, we can also conclude that the new capabilities of ETAP 16 UDM allow us to create more complex plant level control systems for our power generation and microgrid type of systems. And also, as we have seen in some of the examples that we have covered today, we can see that UDM can be used also as a training and an educational tool to be able to teach young engineers electromechanical engineering concepts related to power system analysis. With all this being said, it was a pleasure for me to be able to deliver this webinar to you guys today, and I hope that you guys can use all the new capabilities in ETAP 16 UDM. At this point, if there are any questions, we will stay online and to answer all of your questions. Thank you very much.